I can say a couple things while we're waiting for Adam to. Hi everybody. I'm Richard Otis with the Materials Genome Foundation. Really happy that you are all able to join us here today. So you've heard a bit about our mission. I wanted to mention to all of you that after this workshop, you will get an email that has links to the video recording, the slides, and the workshop material, as well as a workshop survey. So we use your input to help improve this and future workshops. So your feedback is greatly appreciated. And as Zikwe mentioned, if you have ideas for a workshop that you'd like to organize, we'd love to hear from you as well. Thank you and welcome. Adam, back to you.
You are muted, Adam.
Can you see everything now?
Yes, see and hear you now, both. Great.
Perfect. Sorry for the interruption. New laptop, and I had to allow Zoom to see everything. Okay, so my name is Adam Krajewski, and I'm going to present on a work that I've been doing for the last couple of years, almost 4, and it has to do with machine learning prediction of formation energy, but it's much more applicable, and I hope that you're going to appreciate the power of the tools I'm going to present. The other authors of this work are Jonathan Ziegel and Professor Xu. They used to be at Penn State, but since we are running this for quite a while, now Jonathan became a professor at Texas A&M, while Professor Xu went to the Saudi Arabia to Department of Mathematics at KAUST. And I wanted to again say that this work is sponsored by IBM, and we are very grateful for that support. To give you an overview of what I'm going to talk about, I'm going to first talk about, let's say, core information that are needed to understand what we're going to do within the workshop. I'm going to quickly introduce what's conceptual machine learning for materials is. Then I'm going to talk about the limitations of machine learning approaches for prediction of formation energy, because that's quite critical to understanding what models in the literature are doing, what they're not doing, and what PySIPFENN is doing most importantly for here. So I'm going to also talk about what are the default models that you're going to use within this workshop, and our advances in descriptor calculation or feature vector calculation that allow these models to run on atomic configurations. I'm going to also quickly mention a couple of things beyond this workshop that we're going to include in the next ones. Like, for example, our optimizations for dilute structures. I'm going to talk about transfer learning, or how to optimize a model for a specific system. MPTT that Dr. Liu mentioned, which is our database for atomic configurations with almost 4 million of them, that allows us to run interesting methods like Crystal. So to start, what these models are doing is, in very basic terms, they're taking the data. In this case, we are taking atomic configurations, and they're calculating a descriptor or feature vector representation. So we are trying to take a bunch of atoms and put them into a set of numbers where every number has the same meaning for every structure. Within PySIPFENN, that means looking at each atom individually, then calculating a set of features for it, and then averaging it over the whole structure. Then we have some sort of machine learning or AI algorithm. This can be a nearest neighbor. In the case of PySIPFENN, this is just a neural network. It's a deep neural network with many millions of neurons, which by interacting together allow us to have some sort of output that is a prediction for a property. Throughout this workshop, we are going to be predicting formation energy. But in principle, you can, for example, take the same feature vector, which is structure-informed one, and let's say take a data set of Poisson ratios that you have derived from experiments or derived from DFT, and plug it into PySIPFENN to predict that. The reason why we are predicting formation energy is that because we are interested in that in our work. So what are these machine learning approaches to atomistic energetics do? If we look at let's say, energy versus composition or versus a certain system, we're going to see that we have a lot of phases that are present, or a lot of end members of phases that are present in this sort of database at 0 Kelvin. And we can look at specific structures, like, let's say, sigma phase. And we can also look at something called convex Hall, which is a Hall created by the lowest energy structures. And in general, these machine learning approaches are going to either focus on a single phase. This is by far the most common thing that is done in literature right now, because it's very simple. It's easy to implement. You have, for example, 243 end members of sigma phase in a ternary system, and then you calculate 50 of them, and then you extrapolate to the other 250. And it's very good for this kind of interpolation, but it's very difficult for it to generalize beyond, or even impossible, because you're limited to this specific phase. Then there's a lot of methods, like, for example, one of the famous ones a couple of years ago was the LMNet, which calculate the energy or predict the energy of the convex Hall. So again, this is fairly simple to do. You can just input the exact compositions. There's something called periodic table representation, or you can also input some sort of features of these compositions. But the outcome is usually a very highly accurate model, because this is a simple, in the case of a binary one-dimensional object that you're trying to predict. And the limitation of that, it's very good for prediction of where are these compounds, where are the inflection points, but it's not very good for anything else, because it doesn't provide information of what phase it is. And that's usually what we are critically interested in. So then the third type is structure-informed methods, and PySIPFENN is one of them, which are more difficult to do. These are much more complex models, but they give exact information of what you're predicting, and what are the energies, what are the, for example, sublattice occupancies. And basically, this is the kind of methods that can serve as surrogates for a lot of DFT needed properties. So what are the limitations beyond the requirements and of how we are approaching the materials themselves? First, it's very important to understand that these DFT calculations or databases that store them are internally consistent, but they can strongly disagree with each other. There's a very nice archive paper by Citrine Informatics where they compare AFlow, OQMD, and Materials Project. And if you are interested in this subject, I really recommend reading that. But the takeaway is that if you train a model on OQMD, you can't really compare it with a different model trained on Materials Project, because they're going to give very different results. And both of them are going to be close to the truth that they were trained on. Then another thing to understand is that this performance is that we are reporting here, it's on par with DFT usually, and other models are reporting it too. But this is on a test set, so the structures that were not presented to the model in any way, but still within what was explored in these big DFT databases. So they are very biased towards, let's say, iron-based compounds rather than uranium-based compounds, which are not really present in these DFT databases in the same capacity, of course. And one very important thing to think about also is to include the volume or not to do so. So usually the input data is going to include the volume, because that's what your DFT is, DFT output is, you know, the relaxed volume. However, the volume dependent models, they usually have higher accuracy, but this comes at the cost of requiring to relax or nearly relaxed volumes. One very good example of that is Align, which is a very interesting model. And if you are interested in this kind of models, I recommend it. It has very good Python toolset as well. And you know, if you try to move outside it, the predictions can be quite wild. For example, in the case of BCC iron, which is something that is present in every single of these databases, the predictions of the ground state are very accurate, but then as soon as we try to move outside of it, they can get very unphysical, especially on the compressed side. And sometimes if we present it to a structure which is in the same database, but the model wasn't trained on it because it's a newer one, it's the model can think that the relaxed volume is very far off compared to the relaxed volume in the database. And then these results clearly show that you cannot relax volume itself with this kind of models. And why is that? That's because if you train only on the relaxed volumes, the models are generally gonna associate that with the main factor that affects the energetics. And then within PySIPFENN, we are volume independent. So now the limitation that comes with it is that we are not able to relax the volume. The only thing that we are giving you is the energy that corresponds to the relaxed one, but at the same time, we do not require a relaxed volume input. So with the limitations out of the way, we can try to focus on, and we work hard at overcoming all of this, but that's beyond this workshop. So we are gonna show 4 models within this workshop, and we're gonna start with the ones that we are working on for quite a long while, and which are very well optimized to their specific tasks. So the 3 that are based on the feature vector that were described in 2017 paper, the 3 methods that we are using are standard materials model. So this one is basically having the same goal as most of the literature. Look at a test set of structures from a big DFT database like OKMD, and try to predict them as good as possible. In this case, we took 21,000 entries, and we achieved 28 MeV per atom mean absolute error. And there are a couple other models available in the literature that do the same thing. Mostly there's a couple for materials product, there's a couple for Jarvis, for A-flow. But in general, this is what you can expect from this sort of models, around 30 MeV per atom, and fairly, but that's only for the within the database. Then, if you want to predict something new, then you have to do a bit more work. You cannot just create a large deep neural network and call it a day. In our case, what we're trying to do is instead of let's say when we have this true relationship that OKMD tries to approach and explore, our non-materials model optimized network, like the one that I showed you on the previous slide, is going to try to roughly replicate what OKMD or known data is doing. But if we specifically tell the model to be very general, instead of fitting into this small trends in the data, try to be very broad and very approximate. What we can do is we can create a model that is having lower performance within this known data, but at the same time, it's much better at extrapolating to new kinds of structures, like, for example, sigma phase or SQS, which I'm going to show in just a couple of slides. And we achieved that for a couple methods. One of them is automated feature selection. So we are penalizing the model for looking at all of the features of the structure. And we are also having a couple overfitting prevention methods, like, for example, dropout, which hides parts of the network during the training. And the last model I'm gonna mention is the light model. This one is just the neural network 20, or the novel material model I showed you in the previous slide, but it's highly reduced in size at a very low penalty to the performance in prediction. But at the same time, it's much smaller compared to the neural network 9 or 20. And this allows it to run, for example, an iPhone or a small Raspberry Pi with 2 gigs of RAM, which is only like $30. So you can run it all the time if you wanted to, and it's going to be almost free. So with that, I want to move to the last part that's critical to understanding the contents of this workshop, and that's a new descriptor feature vector that we've been developing, and we're going to showcase here is the Krajewski Ziegel 2022 descriptor, and it is derived from Word 2017, but at the same time, we are using the feature selection that I mentioned that we used, that we developed during the novel materials network training, and we combine it with some feature cost analysis. So basically, we are not computing what we don't need to. And at the same time, we are doing some automated symmetry analysis, and we are identifying chemically equivalent sites in ordered compounds so that we don't have to repeat the calculation that would give the same results based on the symmetry. And that's very important in, for example, case of the chromium iron nickel sigma phase that we're going to see in this workshop, and we're going to see how much this one is making everything faster. So you can expect about 5 to 10 times less computational intensity, and also less memory use. So if you're constrained by it, by the memory capacity of your system, which can be really significant if you're running, for example, 100 of these in parallel. This is the descriptor that you would like to use. And right now, PySIPFENN ships with neural network 30, which is the novel materials model or novel materials network optimized for this descriptor. And we are achieving about the same accuracy in the prediction of OKMD subset that we use as test, but it's still experimental. So your mileage may vary if you use this one. Now, the KS 2022 is also optimized in a separate function within PySIPFENN for dilute solutions, and it generates the same exact feature vector, the KS 2022, but at the same time it's about 20 to 40 times faster, because it recognizes which sites which are not chemically equivalent in dilute structure are actually very similar to each other, and they were chemically equivalent before the solute atom was added, and that allows us to generate exactly the same result, but much faster. But this is all beyond this workshop, and it's going to be covered in the future. Now, what will we cover? We are going to show how to install PySIPFENN. We are going to show how to do a very quick setup and run with a directory in which we have structure files. This is something that is probably going to be most interesting to majority of the users, because this is the way you can create a surrogate of a DFT calculation, which is going to tell you maybe not what you exactly should do, but it's going to be a very good guiding principle which you can run in just a couple minutes. We're going to also show some slightly more advanced things that you might be interested in. Like, for example, we are going to look at the 5 sublattice, which is the full sublattice description of sigma phase, which is a topologically closed packed phase in a ternary system, which has 243 end members, something that would be quite costly with DFT. And we are just going to do it in about 20 seconds. Then we are going to also look at some how to combine results from different models. And if you're an advanced user, you might want to train your own model. You might want to put it in PySIPFENN and run all of this together. So we are gonna also cover that, how to add your own model. And during the future workshops, I want to kind of tease you. We are gonna show how to adjust models to specific system using just a few DFT calculations, and how to adjust the model to a general class of materials. Like, for example, if we wanted to create a model for anti-perovskites, we're going to talk about how to use Crystal, which is our data-driven crystal structure discovery method, and how to include PySIPFENN into a thermodynamic database using S-based software that Brandon Bocklund developed with Richard Otis. So the future that I just mentioned is gonna include a few things that I wanted to again tease you about. This is transfer learning, where we are taking PySIPFENN models and that were again trained on big DFT databases, and we are presenting it with just a few calculations. So by adjusting the learning rate, we can stably reduce the error, and just by doing it for a few times, so in just a few minutes, we can create a new model that is having much higher accuracy. Like for example, here we can see that the neural network 20, so the novel materials model, readjusted based on the sigma phase data, with just around 50 of these calculations, we can halve the error while retaining the prediction performance on a very good level on the whole OKMD dataset. Then the materials property descriptor database that Dr. Liu mentioned, and I also mentioned it, is a 4 million experimental or DFT relaxed structures, where we are inputting these structures onto a cloud-based MongoDB server, where feature vector calculators are picking up materials automatically, based on some nodes deployed, based on nodes that we deploy from GitHub. Then these are picked by machine learning modeling nodes, which are based on GitHub handling code and the node repository of the models, and put it back into this database to have properties available for design AIs and inverse design AIs that can in turn put new candidates into the database. So this is a circular design which can automatically grow and at the same time explore new materials. Our development version is live for 2.5 years now, and it has been used in quite a few projects in our group and our collaborators. It has an open web page that I'm gonna link in just a couple of slides. And if you're interested in being a collaborator on this, we have an API that you can use. In general, we cover 93 elements in 170,000 systems. And that includes almost half of all the binaries and 10% of all the ternaries. That doesn't sound like a lot, but again, this is 4 million structures. So it shows at the same time how much information we have and how much information there is still to be explored. And Crystal is, just to briefly describe it, this is a method that uses PySIPFENN for materials discovery. And what we do is we take 4 million structures from MPDD. We select all of the possible compounds which we can substitute, retaining the same stoichiometry ratios. And based on all the permutations of how we can put the elements into them, we get a lot of different candidates. And again, we are predicting energy with PySIPFENN to identify stable candidates, which then we select using some clustering algorithms to be validated with our density functional theory toolkit. And based on that, we can discover new compounds in different systems, or we can identify compounds that were reported but were never identified structure-wise. Like for example, we did in neodymium bismuth 2 case. And without MPDD, if you wanted to run it on your local system, this would usually take about 4 hours. This doesn't sound like a lot, but if you want to do it for, let's say, 100 compounds or 1,000 compounds, this grows very quickly. While with MPDD, it takes about 10 minutes if you use Word 2017, or about 1 minute if you use KS 2022. So very, very nice framework. We hope to release to the public in about a couple months. And it's already showing as a very powerful tool. Like for example, here, you can see these results from machine learning in blue and DFT in the red, while cluster expansion method is shown in green. You can see that in general, cluster expansion is closer to the DFT results, but it doesn't replicate the convex hull shape, which is the most critical part if you want to explore new compounds within a system. And again, this is not just the convex hull search like LMNet, but this one gives you the exact structure that happens to be at the convex hull. And I'm gonna link publications to the neodymium bismuth 2 and aluminum iron in just a couple slides. Crystal is also capable of not only looking for the ordered compounds or with a specific stoichiometry, but sometimes we also used it for finding new compounds in a composition range from experimental methods. Again, we are performing all of the possible permutations where we of specific range of compositions. Using PySIPFENN, we identify the stable ones, and the FTTK validates which of them are the actual compounds that we are observing, and then we can use XRD to validate it experimentally. So this is the slide that has all of the further reading that you might be interested in. We are having the PySIPFENN GitHub, where if you want to use it or if you want to contribute, you're more than welcome to. Just create your own fork, add your own changes, and create a pull request. If you follow workshop.pysipfenn.org, you're gonna see the workshop files, which we are gonna work on in just a couple minutes. And the PySIPFENN documentation is available at pysipfenn.org or at this QR code. If you wanted to learn more about the MPDD and see some statistics over it, as well as try out if the compounds are available in it, you can follow this QR code. And if you are interested in crystal, this neodymium bismuth paper is a very good example. It's a nice ACTAMAT paper, and you can find it following this QR code. But if you want to combine this kind of data that we are going to be generating into your CalFAT modeling, the tools that you are going to probably want to use are SPay, that allows to incorporate these predictions into TDBs very seamlessly in an optimized fashion, and then PyCalFAT to run predictions. So thank you for listening to this introduction. And now we are going to move to the cloud service to actually perform these calculations and play with it a bit. Are there any questions before we start that? There's going to be a Q&A at the end. Okay. Let me stop the share. Thank you, Richard, for the Phases Lab, for the link to the cloud. It's in the chat if you haven't had a chance to log in yet. To answer Sheng Han question, it's phaseslab.com. With an S after phase. Can you see my screen?
Yes.
Perfect. So as we start this workshop, you should see this exact screen showing you all the options that you're given in this pod or computational pod. And on the left side, you're gonna see the folder with the workshop material. So if you go to it, there's a couple different items. One of them is the README, which is the same as on the GitHub repo, and explains what we are going to do. But then there are two more, which are Jupyter notebooks. This is the kind of document that allows you to run Python in a step-by-step fashion while looking at the outputs. There should be two of them. One of them is PySIPFENN examples, and one of them is PySIPFENN examples clean. You want to open the clean one because the other one is already completed workshop. So if you are having any trouble following anything, you can always look at this one with all of the examples completed. But to have a fresh start, we're going to follow this one. So first of all, again, PySIPFENN stands for Structure-Informed Prediction of Formation Energy using Neural Networks. And these links on the top show you the GitHub repository, the documentation, which I have right here, where you can see, again, install instructions. You can see the API. So if you don't know what a function is doing, you can always go here and, for example, click here. What is the get results dicts doing? It returns a list of dictionaries with prediction for each network and so on. You're gonna see what type of the output it gives and what exactly it is. You can also look at more complex functions that we're gonna see throughout this workshop. And if you want to find out more about different projects that are using PySIPFENN, you can move to our group research website. Okay, so as I explained in the introduction, we're going to be taking crystal structures, calculating feature vectors or descriptors, passing them through a neural network, and at the output layer, we are going to have delta H, DH prediction. And in general, this is roughly what's going to happen in a code. It's very high level, so you don't need to perform any complex operations on the data. We start by looking at the install. You don't need to install anything here because everything is taken care of by Richard, who set up this environment. Thank you, Richard, again. And this is only for your convenience if you wanted to install it on your own local machine after this workshop. These instructions, again, are also within the documentation that you can find at PySIPFENN.org. So, assuming you have everything ready, we are gonna start PySIPFENN. And to do so, you first have to import the PySIPFENN and PySIPFENN calculator class. In order to run a cell in Jupyter, you click on it, and then you click Shift Return. This one allows it to run, and now we can see that it was executed because the number changed from an empty bracket to 1. Then we also want to import some additional functions, which are going to help us run everything. These are not critical, but I like this one that prints things nicely, so we can see your results in a more clean fashion. And the collections are useful in one of the examples, or the default dict. So we run them as well. And now we need to initialize the calculator. So what's going to happen here, let's run this. And you see that it printed out a couple of things. The first one is saying that the PySIPFENN Krajewski 2020 standard materials model has been detected because it has a check mark next to it. And it detected them because when setting up this environment, we already uploaded all of the models to the cloud. If you're running it on your own computer, what you would need to do is you would need to go and after typing this, C equals calculator, you would need to download the models from a repository from Zenodo. And this is as simple as running this without the hash. So C, download models, and then C, load models. And you will be in the exact same state as we are right now, with all of the models loaded and PySIPFENN successfully initialized. I'm going to take a minute for everyone to have the calculator initialized so that we can follow smoothly. Let's take 3 minutes maybe to noon 50.
Excuse me, can you say again how you run or how you make this thing work? It's Control Shift, something like that?
Yes, Control Return.
Oh, okay.
Or Shift Return, or Control Return. On different systems, it can be different. But Shift Return always works.
Okay, okay, thanks.
They're actually both work, but one stops the cursor at the current cell, and the second one just skips to the next cell. Shift
Right, that's
enter
usually.
skips, and you can also use the play button at the top of the window to run the cell.
Thank you, Alexander. Ethan had a very good question. Are we meant to uncomment the C download models? In this example, all of the models were already uploaded to the cloud, and you don't need to download them. But if you're running it on your local machine, that's what you would need to do. Also, to elaborate on that a bit, since all of the models are already downloaded, if you tried to run it, it would just tell you that all of them are there. And if you were to try to fetch a very specific model, like for example, this is the light model, and if you're having trouble with your storage size or anything like that, but still wanted to run PySIPFENN, you would want to run this command here. That would fetch only this one, and it's about only 1/30 of the size of all four. Are we having anyone who is still working on this step? Jian, so I got a question. Are the notebooks always available, or shall we lose the access after the workshop? So you're going to lose access to the cloud, but these notebooks are available on GitHub under workshop.pysipfenn.org, and you can also see them within the PySIPFENN documentation if you click on this PySIPFENN MGF PSU workshop, and it has everything that I'm showing here already run. So you can follow it in your own time. Okay, so I'm assuming that everyone has PySIPFENN initialized, and you know what you would need to do if you were running it on your own. So let's move to the simple run from a directory. As again, this is what you would want to do if you wanted to create a surrogate, very simple to use for DFT. And I believe that this is one of the most common applications that people would like to run PySIPFENN with. So the only thing that you would need to do after you have this calculator initialized is to have a directory within your folder with the same with the workshop files, or with your PySIPFENN script or Python script with PySIPFENN. Create a folder like my input files, and put your postcards within that folder. And then just run this kind of function. In the case of this workshop, we are not gonna create any new files. But again, if you wanted to, you can just uncomment this and run everything again, and it would run your personal files that you might want to predict the energy for. during this workshop, we are gonna take files that we use for testing PySIPFENN. So this is the kind of files. We have about 30 of them, which are mostly Sigma phase and a couple others, which we have in the test case files, example input files within the PySIPFENN package. And this function basically imports them as a directory of files. So instead of having all the files placed here, we can just run it directly on what's already included in PySIPFENN to test whether it works. And to do so, we click, and again, we run this one, and then run from directory. What you do have to specify is the directory, of course, but also what is the descriptor that you're trying to use. From my introduction, I showed you the difference between Word 2017 and KS 2022. This one is much faster, but this one has only one neural network that's still experimental. The other one has 3 neural networks that we used extensively in our research. And the mode of calculation is either serial or parallel. Parallel is going to use more cores and it's much faster. But right now, let's just do serial. Importing structures is usually very fast because it's just a couple of small files. And then what we are doing is we are calculating these feature vectors. So it has to look at every single atom in the structure, then featureize it or create a description of all of its local chemical environments, and finally put it all together. So that's a very intensive process, but with KS22 it's highly optimized, and we can even on this server, which has very low speed cores, but a lot of them, we can run it at 3 iterations per second, so about 300 milliseconds. Now, everything was predicted, everything works. We can look at the first, there are a couple variables that this class now possesses. One of them is the input files with all of the names of files that we used for the testing, and then the predictions that it obtained. If we look at the files that we run, these are all 3 of them are sigma phase with 30 atom cells, and the predicted energies are shown on the bottom. If there were more models that would be run, all of them are again loaded automatically. There would be more variables which are ordered in the same order as you saw your models here. And in just a moment, I'm going to show how to output it with the names of the models as well. So you can see now with this function, you can get results dict with names, and it tells you what's the name of the structure that you run it on, and what's the name of the model that was used to run it with the energy next to it. And if you wanted to have it persistent, you can output it into a CSV, like my first results from PySIPFENN, and it should show up right here next to your Jupyter notebook. I see some questions in the chat. Yes, you forgot to run one of the cells. If you're having pprint not defined. Okay, so we have this CSV file with names and corresponding energies, and this is, I believe, what most people are interested in, just having this kind of output where they can put all of their postcard files that would normally be used for DFT and make predictions of the energy. Now,
Adam, could you also state the units and the reference state that you get by default from PySIPFENN?
Yes, sorry, I have it here. In the case of the predictions that PySIPFENN makes, this is of course going to be dependent on the model that you run. In the case of this workshop, all of the outputs are in electron volts per atom. So if you look at this structure here, this is 178 milli electron volt per atom. And the reason why PySIPFENN doesn't round this is that somebody might want to run a different model, for example, for Poisson ratio, and they might want to have a higher accuracy or lower accuracy, and that has to be defined on the network level. Thank you, Richard, for asking. So with that, we can go to some more advanced examples. So in the previous one, we just ran it on a directory, have a set of postcard files which we use, and just run it, just a couple quick functions. But now we're going to do something a bit more interesting. Now, so sigma phase is a topologically closed pack phase. It has 5 sublattices, so it has 5 unique chemical environments where you can place atoms from a single element to 5 elements and create this sort of end members that allow you to then look at their energetics and see if you put these atoms together at this stoichiometry, what's going to be the lowest energy occupation. And also look at the whole Turner diagram and see where sigma phase may form. And within this example, what we're going to do is we're going to first start a software called PyMatGen. If you don't know it, it's one of the best spent times as a material computational scientist learning it. It's extremely powerful. A lot of people who are creating it. I contributed some of my time to improving it, and I highly recommend it. What we're going to do is we're going to import the structure class, which is used for handling structural information. And we are going to also use the space group analyzer, which allows us to look for equivalent sites in the structure. So let's run it. And then what we are doing is we are looking for an end member path. So this can be any of the postcards that we looked at before. In this case, I just picked the first one, but you don't need to specify which elements are on which sublattices. It's going to automatically determine which of them are unique chemical sites. And to do so, we are first removing all the elements. We're just replacing them with dummy species. So we are having this structure, which is 30 elements of dummy species with a specific cell, and then positions of all 30 atoms. Now, we are using the space group analyzer to look for equivalent atoms based on the symmetry data set it generates. And for each of these equivalent sites is going to have one of the other sites assigned to it as the first unique site. So this allows us to create this unique dictionary, which says that the site 0 is the same as 0, 1, 2, 3, 4, 5, 6, 7. Site 8 is the same as 8 and 9. Site 10 is and so on. So we are having 5 unique sites with different numbers of repetitions within this structure. Oh, I see some questions in the chat. What is the meaning of the 0+ after dummy? So I believe PyMatGen just automatically tries to assign the charge to the site, which is 0 charge, and it shows up in this kind of printout. But it doesn't have any effect on the results of our calculations, because right now in the second part of this, once we identified all of the unique sites, we can iterate over all the possible combinations of iron, chromium, and nickel, repeated 5 times. So we are looking for all the possible permutations, which are going to look like, for example, iron, chromium, iron, nickel, iron, chromium, nickel, and there are 243 of them. And then we create the structure list by putting this permutation into these unique chemical environments. And this gives us a structure that looks like this one, where we are having the first sublattice occupied by iron, then the second one with just 2 sides occupied by chromium, then iron again, chromium, and nickel. And this is the structure that we're going to input into the PySIPFENN. And in the case of the first calculation, we are using the run from directory function that requires the directory, descriptor, and mode of calculation. In this case, we don't need to output the files because they're all already in the memory and converted into PyMagen structures. So what we can do is we can just run models on this list of structures we created using descriptor case 2022 in parallel and with 12 workers working parallel at the same time. And the latter function prints just the first 3 of them so we can see how the result look like. So let's run this. And you should see a fairly quick calculation, about 20 of them every second, because now instead of running them one after another, we are running 12 together, and done in 13 seconds. This would probably be even faster if we didn't have about 100 participants right now running on this cluster at around the same time. And then the models themselves are very quick in running these predictions after featureization, and they do it at about 74 predictions per second in this case. And we have all 233 predictions for this model, and we can see the energetics of this TCP phase. We can also output it with the get result sticks, like we did before, and we have the PySIPFENN Krajewski 2022 neural network 30 and the energies it predicted. I see some questions in the chat. Yes, you can either output these structures into cells, or you can store them as postcards. And I see Tobias ask, how does the predicted energy depend on the lattice parameter specified in the postcard file? So if you scale the cell in all 3 dimensions equally, then the thing that you're scaling is only the volume. And PySIPFENN, as explained, is volume independent, unlike some other methods, but at the same time, it doesn't require volume relaxed input. If you scale one of the dimensions, like for example, you take a cubic cell and make it tetragonal, then the energy is going to change quite significantly. If it's for example, a BCC iron cell. So it's gonna depend in this fashion. Now, as I explained, we have different feature vectors, so different descriptors that we can use, and PySIPFENN is built to enable a few different ones, and we want to be able to rapidly deploy models within PySIPFENN. That's some more questions. My prediction rate is 89 per second. If you do it on your own laptop, it might be much faster. On my MacBook, it's about 100 predictions per second if I run this code. But if you do it on the cloud, it's going to very highly depend on how many people are running it at the same time, because participants are sharing the cloud. I got very slightly different result after 5 or 6 digits of decimal points. This shouldn't happen unless maybe it's possible that these are just not in the same order. But we may look at it after the main component of the workshop during the Q&A. Is the predicted energies how predicts the energies. How do I get the corresponding formula? If you wanted to get a formula for each one of these structures, you can go to the structure list, and for each one of them, for each element of that list, you can ask for the formula variable. You can see it in the documentation of PyMatgen, and if not, I'm gonna help you with that after the end. Okay, so going back to the workshop, as we alluded before, we want to be able to deploy a lot of these models on a lot of structures, and the feature calculations, as you've seen here, they are generally the slower part. In the case of Word 2017, which we are going to run in just a moment, it can be 100 to 1,000 times slower compared to the neural network run, because these are just very simple operations. So you just have to pass information for a neural network and to get the output. So we want to limit the number of times we have to calculate the structures. And that's why generally we would like to reuse the same feature vector for the model, but it's not always possible, because sometimes, for example, the feature vector might not have a feature that you need. An example is that PySIPFENN doesn't include the volume information. And if you had a property for which you had a data set of volume-dependent data points, and wanted to run it, that wouldn't be possible, and you would have to use a different feature vector. However, sometimes we want to be able to also incorporate some other things like magnetic behavior. And if you want to use a very specific model, then there is usually no other way than to run that feature vector. That's why here we were running KS 2022, for which we had this new model, but we want to roll back into the legacy model, or the ones that we already have established well in our research, like the neural network 9, 20, and 24, which I described in the slides at the beginning. So we want to run this Word 2017 model. Let's do that. And now, first of all, you're going to see that we usually have to run it with a lower number of workers, because it uses much more resources. In this case, I run it with 8, though usually I would recommend running it with only half of the workers. And it's gonna be taking about a minute for it to run and get everything together. The reason why it's not showing up the calculations very quickly is that it has to run 8 of them parallel, and it waits for the results from the other 8 before it shows the output. In the meantime, I'm going to answer the questions in the chat. Is it possible to run the code on several nodes, not cores? So we do that. One way to do it is to define what are your structures that you are interested in, and just define different sets on different nodes and start the same calculation together. So for example, define 5 different sets of data and then deploy it on 5 nodes, each one of them running 32 threads on 32 cores. In the case of MPDD, the way we have it set up is that the infrastructure is very decentralized. So instead of us defining what the PySIPFENN has to run on, we are telling the each computing node to connect to the database, ask it for what should be computed, then take these structures, compute them, and put them back. And the advantage of this kind of processing node database interaction is that we are never limited in how many of these we are running parallel. We can run 100 nodes and calculate everything within an hour, or we can run 1 node and calculate everything within 100 hours. So it's fully parallelizable. And even infrastructure can be different. For MPDD, we are having a VM, a virtual machine set up at Penn State, which uses all of its cores to constantly crunch numbers and make predictions in MPDD. But at the same time, at my home, there is a small Raspberry Pi that also runs predictions, but only using the neural network 24 because that's what it can do. So you can scale it to different hardwares as well. Let's see how we are doing with the computation. Oh, perfect. On my machine or my VM, everything is done. I'm going to answer the other. Oh, thank you, Philip. I'm going to have a long sip of coffee before we move forward, so that everyone can have their things done before I move on. Okay. So we see that the same set of structures that previously took us 13 seconds now took us 2 minutes and 46 seconds, so much longer. But at the same time, it allowed us to run the models that neural network that KS22 couldn't be run with. And this is the standard materials model trained on to be the best at OQMD. Then the neural network 20, which is the novel materials model, trained to extrapolate to new knowledge, and neural network 24, which is created to be very fast. You can also see how much faster it is at making predictions. In the case of neural network 9 and 20, it ran 66 predictions per second, but in neural network 24, it ran 500 of them. Doesn't matter for 240 structures, but if you try to run it on 10 million, this is getting quite significant. Trivala said, I got a message that said not possible to save. Richard, can you help with that? Thank you. Okay, so we have these results. Now, again, let's get the result dictionaries. We can see that the models are generally disagreeing with each other slightly. And that's to be expected because they're trained on the same set, but with different tasks in mind. Is this, I was wondering about the SQS calculations. Is special quasi-random structures methods? Did you compare your results to SQS calculations? Yes, that's what I have in just a couple lines below. Is this applicable to more than ternary phases or high entropy phase? Yes, so you can run it on anything. The set of structures within the training set, which is the OQMD, it's very broad. We do run it to predict intermetallics with high entropy alloys. We do run it to predict SQS and also MCSQS, which is the approximation of SQS structures, and incorporate that into the thermodynamic databases directly. Okay. If you wanted to combine the two, because you see that first result we saved was for neural network 30, and these are for the 3 other networks. With Python, you can just do it quickly with a command like this one, where we are combining result 1 and result 2 for every result in these two dictionaries, or a list of dictionaries. And we see all of the results combined. If you wanted to run a different model, like for example, Poisson ratio, or you wanted to run band gap predictions, this sort of function would quickly allow you to combine the results. And you can also add your own labels. Like for example, here, we are gonna take configuration and add all of the elements that we used for each permutation in when we were creating these structures. So let's have a look. And we see that these first 4 correspond to the iron, chromium, 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 sublattice configuration, and so on. I see a question. How about oxides with multi-component? So I believe that should extrapolate. because there's a lot of oxide data within the OQMD data set, and I believe it should work. If you are interested in some specific system, I can also check what's the coverage of that. Just send me an email. And lastly, we can look at the DFT comparison. So in the case of sigma phase and looking at the sublattice occupancy, the critical feature that we are most interested in is the Pearson correlation, or R value. How well do we order these sublattice occupancies so that we can compare which one of them is more preferable than the other. And we can see that with the neural network 9, we are having R value of 0.377. Was the SQS your initial input to predict the energy? No. So at the time of the training of this data, of these models, I'm not aware of any SQS within the training set, as well as no OQMD sigma phase coverage. So this is the worst case scenario for metallic alloys, and you can see that the error is in the case of neural network 9, this is substantially higher compared to what was the error for OQMD, which was under 30 MeV per atom. Now it's 57. While the neural network 24 happened to be very low, and neural network 20 is about the same as it was. At the same time, neural network 20, which is the novel materials method, novel materials model, has substantially higher R value, or is better at ordering this in a linear fashion compared to the database energy, which is critical for predicting the sublattice occupancy. And now the last part of this workshop is how to add a new model. So let's say that you created a model, you trained it, or you retrained it with the transfer learning I kind of teased you about before, and which we hope to include in future workshops. This is very easy if you're a machine learning scientist. You just need to create your neural network that uses one of these two feature vectors, either KS 2022 or Word 2017, and output your model into something called ONNX format, which is the open source format for neural networks. It's you can export it from PyTorch, which is the ultimate framework we run these models in, or you can you can use another flavor you want. You can use TensorFlow, you can use Keras. In the case of PySIPFENN, we actually used MXNet, which is much faster, or was much faster in the last few years compared to PyTorch. But PyTorch is much easier to run, and that's why we are using it to distribute our tools to the community. To add your model, if you have write access to the PySIPFENN directory, so you have it installed on your local machine, you can just go to that directory, and within the models PySIPFENN directory in PySIPFENN, you can find the models.json file and put your own model into that JSON file, like that. My PySIPFENN MyFunNet 2023, let's say, nickel superalloys, and explain what it is. It's a neural network 30 re-optimized for nickel superalloys, because that's what you created your data set for, and what descriptor it uses, and the node that's gonna be there just so other people can know, or you can have your nodes there for future reference. And then put this model in ONNX format into this model PySIPFENN directory. And with that, you should just be able to do C equals calculator, and everything is gonna work out of the box even with this notebook. So you don't need to write your own scripts or your own notebooks. It's gonna give you all the results. But here we don't want to change the PySIPFENN installation. And you might not be able to do that if you're running on some high performance computer, like here where we are having this workshop. So what we are going to do instead is we are going to add a custom model in a slightly different fashion. What we are going to do is we are going to copy one of the models, the neural network 30, and put it in our folder here where we have the writing access. And we are going to call it, like we did here, my fun network for nickel superalloys. So let's do that. That should be fairly quick. And the model appeared here in your directory where we are working. And now, again, we are not able to modify the models.json file, but after adding this model here, we can add it to the calculator by loading it in a custom fashion, specifying the network name, which has to correspond to the file name here, model name, which is explaining what it is, and this is what's going to show up when we load it, and what kind of descriptor it uses, and where it is. A dot indicates that we are looking for the working directory or our home directory where we are working. There we go. It takes a second to load it because it's fairly large, and these supercomputers are probably right now very highly doing their best because 86 people are trying to load this. But if you're doing it on your own computer, on my laptop, it takes about 2 seconds to load that network. So this is usually not something to worry about. The number of the networks or their size, as long as you have enough memory in your system. Okay, so we loaded the model. It said that it's the neural network 30 reoptimized for nickel superalloys. And now we are just doing the same things we did before. We are running the models using the structure list, using the case 2022, and in parallel using 12 workers. Just a couple seconds. And we can combine the results. Boom. So now we see that our iron sigma phase has the same predictions with the nickel superalloys network as with the neural network 30 because it's just a copy. Okay, let's see the chat. I was wondering about the limitation of PySIPFENN tool. Could you elaborate on that, Sandeep? And in the meantime, oh, the size of the systems. Okay, so there is no limitation per se. If you can put it in the PyMagen structure file, it's gonna run. If you run it with the Word 2017 descriptor, one of the features, which is the WC parameter, is gonna scale non-linearly. And that one is going to take quite a while to calculate if you give it, for example, 120 atoms. But case 2022 shouldn't take too long. If you're interested, we can actually test that after the Q&A. How to predict Poisson ratio with this model? So in order to do so, you would have to have a data set of Poisson ratios. You could create it, for example, based on Materials project, which gives you that information, or Jarvis from NIST, or I believe for some of the AFlow entries, it's also available. And after you create such a data set, you would need to use some sort of machine learning framework like PyTorch to make these predictions. And then you could input it into PySIPFENN and use it as a running tool for these models. But it's not shipped with PySIPFENN yet. How to get the convex hull from this data? If you wanted to create a convex hull, my recommendation would be to use PyMatGen phase diagram, a plotter, which plots 0 Kelvin convex hulls in 2 dimensions and in 3 dimensions, where you can move it around. If you want me to point you to specific resources, just shoot me an email and I'm happy to do that. Could you please specify the reference you use to calculate the formation enthalpy? Okay, so when we are doing this sort of trainings, again, as I mentioned before, these databases do disagree with each other. And for example, in the case of chromium, I believe OKMD uses ferromagnetic chromium, while Materials Project or Jarvis are going to use anti-ferromagnetic chromium. And because of that, that's one of the reasons, in addition to DFT settings, why these databases are going to disagree. And when we are doing machine learning training on these databases, we inherit all of the reference states and all of the assumptions that they had in them. So for PySIPFENN, all of the networks that are included in the Zenodo repository right now are trained on OKMD, so the references are going to be exactly the same. Then the question from Gukan. Could you please explain again the meaning of res 3 and res 1, 2 in the last cell? Okay, so this is just let's say a shorthand notation, and this is more of a Python thing than PySIPFENN itself. But what happens here is we are having 2 lists. One is the results combined labeled, which we created at the end of running Word 2017 on the 243 members, and we have the result 3, which is our result that we've got from the last run with our custom network and the previous one. And a zip iterator is just wrapping the 2, so we move through them together. And I named this one res 1, 2 because it combines. It's already combined result from run 1 and run 2. Run 1 being neural network 30 and run 2 being the Word 2017 run for the 3 networks, and then result 3 is the one here. And this operator here is just creating a union of the dictionaries which we created. So this is just combining dictionaries. I don't understand the difference in the results, especially the negative one. SIPFENN neural network 20, 24. Okay, so as explained, these networks are optimized for quite different purposes. Neural network 20 is going to try to be best at extrapolating from what we had in this big DFT databases to structures that are not explored before. And in the case of iron, chromium, nickel, sigma phase, this is the one I would trust the most. The neural network 9 is the one optimized for a prediction within the big DFT database or their scope, and neural network 24 is like 20, but optimized for speed. The reason why you're seeing neural network 30 being very high here is that this is still in active development, and this one is not optimized yet very well for the extrapolation. In general, what we will see with this neural network 30 within let's say test set of OKMD, the performance you're getting is very similar to neural network 20, but again, in some cases, like in the iron chromium nickel sigma phase, we are seeing that it performs much different than we were expecting. So this is still in the works. How do I know which one I should take? The choice is going to depend on the kind of materials you are looking at. If you're looking for something that you would normally look for, let's say if you think that this structure is in big databases like OKMD, or this composition that you are looking at is in OKMD, then I would pick the neural network 9. And if you don't think they are, then I would pick neural network 20. If you think that your material is fairly exotic. And neural network 20 is only for when you don't have resources to run the other two. In general, this big database are going to cover a lot of materials of interest, but as I mentioned within the MPDD slide, only half of the binaries on the periodic table are in all of them. So you certainly every once in a while hit a system where which might not be explored at all. Like for example, neodymium bismuth 2 laid in a system in the binary that wasn't reported in DFT at the time when we discovered the structure. Okay, Jian said, can we use PySIPFENN to predict pooled Y diagram? In general, PySIPFENN gives only the formation energies at 0 Kelvin at the moment. We are working towards extending it to find the temperatures. But if you can get something predicted with DFT, then generally for periodic structures in DFT, then you can do it in PySIPFENN as well. Sandeep, is it compatible with both the old and the new API of PyMagen? So PyMagen generally allows you to query materials projects for both structures and energies, and what you can do is you can use PyMagen to get a list of structures, and then that list of structures can be directly inputted into PySIPFENN. And it's the structures in old API and in the new API are outputted in the same format. So it should run without any difference. Then the next question is from MD Ali. Sorry, I might missed this part. I understand we are predicting the formation energies here for a specific atomic configuration. What does the configuration refer here in the prediction result line FE, 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 FE? So if we go a bit higher within this workshop notebook, we established that within the structure of sigma phase, we have 5 unique sites, which are then repeated in the structure based on the symmetry. So if you put an atom on this site, the symmetry is going to populate all of the others. And when we were creating all of these possible occupations of end members, we are placing a specific atom or specific element at each of these sites. So iron, chromium, nickel, and based on that, we were creating the actual atomic configuration. which was run through PySIPFENN. So this string of 5 elements corresponds to this occupancy configuration. Does PySIPFENN also accept old postcard files without the line containing the atomic types? I believe so. If you show me a postcard file which you have in mind, or example of such postcard, I might be able to tell you. Yes, I believe Richard is recording and is going to be made available.
That's
Also,
correct. It will be made available.
Perfect. Also going back to Philippe's question, we are not only accepting postcard files, but also other formats like CIF files and others. Anything that PyMatGen can accept is also going to be accepted by PySIPFENN. You can also use Jarvis atoms with one additional function. Then the next question in the queue is Alexander. Is it correct that the similar to CE, these models work only on specific prototype lattices? Volume is invariable. How about atomic positions? So you can actually do local relaxations with PySIPFENN. We tried it a couple times. In general, there is no data set that would allow you to do it very accurately right now, and we are still in experimental phase doing that. But this is a future direction where we are going to be able to create this sort of local atomic relaxations. Is it? But to answer your question, whether it's similar to cluster expansion, no. So you can put any sort of atomic configuration. We ran it on metallic glasses, which were first relaxed with MD, and we were doing diffusion with PySIPFENN with quite interesting results. So if you can put it within a lattice and specific atomic positions, it's gonna run. No limits there. Jian, NN24 seems to work best for the particular case of iron, nickel, chromium. Do you know if there are any other cases where the model works badly? I mean, are the model performance dependent on the type of material, pure metal, oxide, nitrides? So we are adjusting our models to specific classes like this one. And this is going to be covered in one of the future workshops. But the models that I'm showing here are very general. They should run on any class of materials with about equal performance or performance expectations. If we go down a bit in the notebook, we see that neural network 24 is having the lowest error. And the reason for that is not because it's optimized, but it just happens to be very high performant on the sigma phase. But at the same time, if you look at the R value, so how well it ordered different sublattice occupancies, it's actually slightly worse than the neural network 20. And that's the feature that we cared about a lot in this study. Triumph Villa asked, can we use PySIPFENN to predict other properties, density, mechanical properties based on materials project or QMD database? So it should be, again, quite straightforward to run your models within PySIPFENN based on your own models again. We are not shipping PySIPFENN with any of these models, but you can do so. At the same time, you mentioned mechanical properties. We are in active development of models that are going to enable you to calculate derivatives of strain or energy strain contribution to the energy, and then based on that you could predict things like, for example, bulk modulus or Poisson ratio. But that's not published yet. Oh, what are the requirements to custom networks? So that's a very good question. So the only requirement that PySIPFENN presents, if you want to just put your network in and run it, is that it uses one of the feature vectors that are implemented already, or you can actually add your own feature vectors and do a pull request if you are interested in contributing to PySIPFENN. So basically, you want to create a network that takes one of these. So you can actually use even PySIPFENN to serve as a source of data to train. You just would need to input your structures, and then you can run one of the functions within PySIPFENN. If you go to the API, you can find the PySIPFENN descriptor definitions, like for example, KS 2022 or Word 2017, and they're going to have a function called generate descriptor, which takes any PyMagen structures and generates a 271 length NumPy array, which allows you to then train your own models. And within PySIPFENN, you can actually also look at what are all of the. Oh, sorry, something jumped. Either way, you can look at all of the descriptors calculated for these structures, and then train on them as well. And should the output always be the H? No. So this is the delta H, or formation enthalpy or formation energy. This is just because we are interested in it. We are a computational thermodynamics group. We are interested in creating CalFAT databases. We are interested in discovering new materials based on their stability, and that's what's interesting to us. But at the same time, PySIPFENN is able to handle any model output. It can be band gap, it can be Poisson ratio, whatever you would like. And if you put your model into PySIPFENN, it's just gonna be right next to all of the others with different meaning of the output. Philippe asked, and the dielectric constant. The general rule of thumb is that if you think that your feature or your property is structure informed or depending on the structure and the composition, of course, you should be able to use one of the feature vectors within PySIPFENN. And if you're getting poor performance, or if you wanted to add some new property, you would need to modify. But as long as it works, you might just be able to add your property, whatever the property is. Faride said, "Hi, thank you very much. I started the machine learning as a self-studies, and I want to investigate the CO2 electroreduction. This is my pleasure if a professor accepts me to work together." Well, one thing is that I'm not a professor. I'm a fourth-year PhD student. I do have quite a few years of experience in machine learning and computational material science. But if you are interested in computational materials, please apply to Penn State. And if you're a student still looking for PhD, please apply to Penn State. And Dr. Zikui Liu is here, and you can email him. His email is at the end of this workshop right here. Jian said, how is the model neural network 24 performing with amorphous structures? As I said, all of them should be performing about the same, or can be assumed to perform the same on all of the kinds of materials. They are not optimized towards any specific type. One thing to keep in mind is that OKMD primarily contains ordered compounds, so amorphous structure is going to be quite far from the training set, and your results are not to be fully trusted. How to prepare the database with new properties? Where should I put the property value as an input label in the model? This is a bit more of a complex problem beyond maybe explanation here. But what you want to do in the simplest case, you might be able to, depending on the size of your data set, if your data set is under let's say 10 or 100,000, then you should be able to just have it in a CSV file, and based on some machine learning framework, you should be able to have these features in one column, and then your properties in another column or columns. And usually I will recommend PyTorch to get started. And then you can either have some additions to it that allow you to do automatic neural network creation, where it's doing something called hyperparameter optimization, and quickly get the outputs. Farideh said, "Thank you very much, but I finished my PhD." Oh, sorry if I sounded like I was interested in collaboration. Maybe I took it wrong, but please, if you're interested, then send me an email. But the announcement was more general. If the database consists with a PBC structure, the question is okay. Can you use more SQS data points to improve the machine learning model results? Yes, so that's something we also do, and if you are interested in that, it's going to be covered in one of the future workshops. Because we are working on incorporating that capability within PySIPFENN directly, so you could just give it, like, let's say 10 or 20 data points coming from DFT, and adjust the model to that specific system or specific kind of structure directly. Are there some specifics in the neural network architecture you use, or everything special is in the descriptors? So we designed 27 architectures based on Word 2017. And this design was one of the most time-consuming parts, making sure that it's optimized. It's also, remember that at the time when we were doing this, starting in 2019 with the Neural Network 9, it cut down the error by 40% compared to the best at the time network. So this was just an extensive effort to do so. But at the same time, the ratio between how important the neural network is, or how important the machine learning algorithm is, versus the feature vector is gonna depend on the kind of property you're trying to predict. Is it easy to predict based on the features, or is it difficult? And it's also gonna depend on whether you're trying to incorporate some let's say feature selection within the architecture, like we did with the novel materials model, where something called L2 regularization was used on the input layer, effectively saying to the model that I prefer the model that has, let's say, 5 or 10 MeV higher error, but use half of the features or half of the descriptor when it's running, so that it can be more generalizable. Oh, my throat is dying, but I can take maybe 1 or 2 more questions. Okay. Again, if you are interested in this, or you want to ask any other questions, you can shoot me an email or shoot Dr. Liu an email. And also within the workshop, you can within the PySIPFENN repository, you can go here to issues, and you can just ask a question by creating a new issue. And I'm gonna do my best to respond to everything.
All right, excellent. Adam, thank you so much, being very generous with your time today as well. And I thank the participants also for hanging around. I know we're over time. I think, as I mentioned in the chat a few times, there will be a post-workshop email. That email will include links to all the material you saw here today, the recording of the workshop, the slides, the Jupyter notebooks that you saw, as well as other relevant links and references. If you, in addition, there will also be a link to a workshop survey. We use that to your feedback to improve this in future workshops. And also, we're happy to hear your ideas about future workshop topics also. So I think without further ado, we can conclude here. Professor Liu, did you have any closing remarks?
I don't have. I want to thank Adam for the wonderful presentation, and I hope everybody learned something new, and I hope you use them in your work. And as both Richard and Adam mentioned, we're looking forward to hear your comments and maybe even develop future collaborations. Thank you. Thank you for the participation. With that, I think we conclude the workshop. Thanks.
Thank you
for
very
the
much.
presentation. I appreciate such a great audience and a lot of questions. I do like answering questions as long as my throat works.
All right.